We're going to wrap up our discussion of the concept of equilibrium by talking about something called Le Chatelier's principle, which is the idea that when you have a system that is already at equilibrium, you can apply stresses to that system and the system will respond by trying to get back to equilibrium again. You can think of the idea of pushing something and then the system or whatever it is pushing back at you. That's an analogy to Le Chatelier principle. And so what kind of stresses can you apply to reaction that is at equilibrium? You can change its concentration. For example, you can add more reactant or add more product. We can change the volume of the container or add more water or evaporate the water if it happens to be an aqueous reaction because that would change the volume. We can change the pressure if this happens to be a gaseous reaction. We can also change temperature. So all of these are stresses that you'll see have certain effect on the reaction itself. Some of them might have no effects on the reaction. So we'll investigate each one of them. We'll start with the idea of changing species concentration. And again, that just means we're either adding or removing reactants or product. So adding reactant or removing product have exactly the same effect. And in this case, it would be a right shift, which just means that system will make more product. If you remove product, same idea would happen. Now that you're out of equilibrium, you need to make more product in order to get back to your previous equilibrium. So that's what the system is going to do. If you remove reactant or add product, then the system is going to shift to the left side because you're removing reactant, you're going to need to make more reactant. That's a left shift. If you add product, too much product on the right side, it needs to shift left to consume some of that added product. Instead of talking about it qualitatively, you can also see it quantitatively. So for example, here is a reaction that has a K of 10, and the equilibrium constant expression, of course, for this reaction is simply just P concentration over R concentration at equilibrium. One possible equilibrium concentration is 10 molar of product and 1 molar of reactant. Now let's say you add some more reactant so that now your reactant is 2 and your product is still 10. Which way will the reaction shift? We know that our new initial condition is 2 of this and 10 of that. If we calculate our Q, that's 10 over 2, which is 5. Now 5 is less than the K, which is 10. So if Q is less than K, reaction shifts to the right, which is exactly what we said earlier when we were thinking about this qualitatively. We said that if we add reactant, then we're going to see a right shift. Now let's see how changing volume affect the reaction, whether it's a left or a right shift. I'm going to start now looking at it quantitatively. So let's say my reaction now is R goes to 2P. The expression of the equilibrium constant is going to be P squared over R because the coefficient of P is 2. And let's say the equilibrium constant has a value of 25. So at equilibrium, we have 5 mole of product, 1 mole of reactant, and the container is 1 liter in volume. So then if you work that out to concentration, you will get that K equals 25, okay? Now what happens when we reduce the volume to a half liter? If you reduce volume, you keep number of moles the same, your concentration is going to change, right? So if we go to the right side here, and our new product concentration is going to be, number of moles is 5, the new volume is half a liter, so that's 10 molar. Our new reactant concentration is 1 mole over half a liter, that's just 2 molar, okay? Now, what you want to do then is calculate your Q, right? The expression of Q is the same as the expression of K, which is P squared over R at initial concentration. So it's 10 squared over 2, and that's 50. Now remember what we said, our K was 25, so our Q is bigger than K. So which way will this shift? It will shift to the left in this case. So for this specific reaction, when you reduce volume, your reaction is shifting to the left. And you can work out the same situation for the same reaction if you increase the volume to 2 liters. So instead of changing it down, you're changing it up from the original volume of 1 liter. You can work out the concentration here. It's now 2.5 and a half as a result of that new volume. So the Q becomes 12 and a half, which is less than the K, which is 25. So therefore, there's a right shift in this case. So you might think, okay, that's great. You know, we now know that if we decrease volume, it's a left shift. If we increase volume, it's a right shift. Turns out that's not always the case. Let's look at another reaction. Here's a reaction where it says 2R goes to P. And the expression of the equilibrium constant is going to just be P over R squared. And let's say the value of the equilibrium constant is 10, okay? One possible equilibrium situation would be 10 moles of product and 1 mole of reactant, and we're in a 1 liter container, okay?
Let's analyze the same situations. What happens if the volume is reduced to half a liter?
And then what happens when the volume is increased to 2 liters? Here's the interesting thing. If you reduce the volume to half a liter for this particular reaction, your new concentration is going to be 20 and 2 for products and reactant. If you plug that into your Q expression, you end up getting a Q that's 5. But that's going to be less than your K because your K is hen. So if Q is less than K, then it's a right shift. Notice that that's exactly the opposite of what happens in the first reaction where we say the volume is reduced, we see a left shift. Now we say volume is reduced, we see a right shift. When you increase volume here, you'll find that it's a left shift, which is exactly the opposite of what we saw earlier. When volume is increased, we saw a right shift. So what's going on here? Is there a pattern to this, or do we have to do these type of calculations every time? The pattern is depending on which side has a higher total coefficient. That's what's going to determine which way it's going to shift. Now, remember that because we're talking about volume, you need to first only look at aqueous or gaseous species, right? Because remember that for solids and liquids, their concentration don't change, right? Now, if you're decreasing in volume, it's going to shift towards the side
That has fewer particles.
mole, which is the lower total coefficient. That's the side that it's going to shift toward. And why is this?
When you decrease volume,
Concentration would
increase.
How does the system return to equilibrium? It has to decrease its concentration. In order to decrease concentration, you're going to have to make fewer particles. And so that's why you're shifting to the side with
Fewer particles.
same concept here. If you increase
Volume.
now your volume is bigger, your concentration is going to drop. So you want to bring the concentration higher. The only way you can do that is if you make more particles. So that means you're going to shift towards the side that has higher
Total coefficient. Let's see how these explain the shifts we saw earlier.
So if you have R goes to 2P, if you decrease volume,
Concentrations would increase.
it's going to shift to the side with fewer particles, which is to the left side. And that's exactly what we saw. When we reduce the volume, see a left shift, okay? So you should be able to reason this out, both qualitatively, like we just did,
or quantitatively,
as we did at the beginning of the discussion. Let's now talk about pressure. So pressure is a little unique because there's really a few ways to change pressure.
It's important to keep in mind that we're only talking about gases.
Pressure of the gases can be changed 3 different ways. The first is just by either adding or removing a gaseous reactant or product. The way you predict the shift in this case is the same exact way as what we had discussed earlier in this portion of lecture, okay? So if you add reactant, you expect it to shift to the right. If you remove reactant, you expect it to shift to the left. Now, a second way you can change pressure is by changing the volume of the system. So if you make the volume smaller, then the pressure will go up. This is Boyle's law, right? When we talk about ideal gas. If we increase volume, and the pressure is going to go down. The way you analyze situations like this when pressure is changed because the volume is changed, to go back up to our discussion about volume just now to predict what happens
when pressure changes because the volume is changed.
Now, the third situation is the new one. This is if you add inert gas to a reaction mixture that has a constant volume. You might wonder why it's necessary to add an inert gas, which by definition is a gas that doesn't react with the gases that are already in there.
This is often because oxygen, which is present in air, interferes with many chemical reactions. One way to remove oxygen is to
push that oxygen out with another gas, but you don't want a gas that reacts with the gases that you already have in there. So let's say I have some gases floating around here, but then I have some oxygen on the top and I need to get rid of the oxygen because I don't want that oxygen to interfere with my reaction. So I start pumping in a new gas that is inert. It could be helium, it could be nitrogen, right? So by having that nitrogen gas in the container, it's going to increase total pressure, right?
But this turns out not to affect the equilibrium in the reaction,
because the nitrogen itself is not reacting with any of the particles.
And this change in pressure comes from the increase in the nitrogen particles, not from the change in volume. So effectively, we don't have any change in reactant or product concentration, and we don't have a change in volume. Because of that, the system is still at equilibrium and there is not going to be any shift when you're adding an inert gas.
Last parameter we can change is temperature. So let's say we heat it up or we cool it down, okay? So what temperature affects is energy. You might recall again back to Chem 11 that what we call thermal energy, which we also discuss in our kinetics chapter, is the energy due to the motion of the particle, and that gives us the temperature of that
system, right? So when we heat or cool down a system,
what we're doing is we're changing that thermal energy. And so we need to look at whether the reaction is exothermic or endothermic.
Exothermic is when the delta H is negative,
which means it releases heat.
And endothermic means it has a positive delta H, which is absorbing heat.
So one way to think about this is just to say that if it's exothermic, I have energy or heat being released, so it's on the product side. Whereas if it's endothermic, I have energy or heat on the left side as reactant because I'm absorbing
energy.
Now, once you see it that way, when I'm increasing temperature, effectively what I'm doing is adding energy. So if I add energy to an exothermic reaction, what's going to happen? Well, because it's a product, it's going to shift to the left. Whereas if I'm adding energy to an endothermic reaction, it's going to shift to the right. Now, what happens if you decrease temperature? Well, that's the same as removing
energy.
If I take away energy from an exothermic reaction, it's going to shift to the right. Whereas if I remove energy from an endothermic reaction, it's going to shift to the left. Okay, that's the qualitative way of looking at it. The more quantitative way is given by something called the Van Hoff
equation,
which I'm showing here on the lecture note. And the form of the Van Hoff equation is ln of K2 over K1. Now keep in mind that these are equilibrium constants. It's just the equilibrium constant that you measure when you're running the reaction at temperature 2, and then equilibrium constant 1 is when you run the reaction at temperature 1. So ln of K2 over K1 is equal to negative delta H standard over R 1 over T2 minus 1 over T1. Now, you might look at that equation and remember another equation that looks very similar to that. I'm going to write this on the top here. ln of K2 over K1 equals to negative EA over R 1 over T2 minus 1 over
T1.
And of course, that's our
Arrhenius equation.
And in fact, if you recall, the equilibrium constant and the rate constants are related. We had discussed it early on when we're talking about how in elementary reactions we can connect those two constants together. The other thing we remember is that we can also connect the activation energy with
delta H using the reaction mechanism.
So recall that forward and reverse reaction mechanism can be used to calculate the delta H of reaction. If you use both of those concepts, you can actually derive the Van Hoff equation, which is this one right here, using the Arrhenius equation, okay? But I'm not going to do that here. I'm just going to show you this equation and explain that we could use this equation to calculate the specific value of equilibrium constant when you change temperature. So if I were given temperature 2 and temperature 1, and I'm given the delta H, and one of the case,
I can calculate the other equilibrium constant.
Right? It's just the same way as you use the Arrhenius equation to make your calculation.
Let's apply this concept of Le Chatelier principle to an example.
So we have an equilibrium between oxygen in the molecular form and ozone. And then the delta H of the reaction we were told is 284 kilojoules. So what would happen if I were to increase pressure by decreasing volume? So again, think about what happens when volume goes down, concentration goes up. If concentration goes up, I'm going to shift to the side with fewer particles because I want to bring that concentration back down. So that means I'm going to shift to the right side, okay? So that's the answer for the first one, shift to the right. What happens if I add
more oxygen
at constant volume? Well, if I add reactant, it should shift to the right side as well. So that would be a right shift for number 2. What about decreasing temperature in this case? This is an endothermic reaction. So you can say that reaction is 3O2 plus energy goes to 2O3. Energy is on the left side, a reactant in this case. So if I decrease temperature, that means I'm removing my energy. Reaction should shift to the left. What about adding a catalyst? This is not something we've discussed before, but you should think about what a catalyst does. All it does is it speeds up reaction, which means that it gets you to the destination faster. All it's doing is get you to the equilibrium faster. It doesn't really change the equilibrium. So if it doesn't change the equilibrium, then the system will not do anything. It will not have any change at all, okay? Because the catalyst doesn't do anything to its equilibrium position.